Hello, in this lecture we will find the area of a circle. In the drawing we have a circle and inside the circle we have a shape, angle ADC. This angle is a right angle, it equals to 90 degrees, and also angle BCD, this angle equals to 90 degrees, it is a right angle, and side AD of this shape is 4 units, while side DC equals to 6 units, and side BC of this shape equals to 8 units, and we want to find out the area of this circle. First of all, I will explain you what are one-sided angles. The term of one-sided angles. If you have two lines, line A and line B, this is line A and this is line B, and line C intersects these two lines, line C in the red color intersects line A at this point, while line C intersects line B at this point. Actually, angles alpha and beta, those two angles alpha and beta are defined as one-sided interior angles. Okay, I write it down. Those two angles alpha and beta are defined as one-sided interior angles. One-sided interior angles. Okay, those two angles alpha and beta are defined as one-sided interior angles. And why are angles alpha and beta defined as one-sided angles? The reason for that is because of the fact that alpha and beta are located at the same side of line C. Both of them are located on the left side of line C. For that reason, they are defined as one-sided angles, because they are located at the same side. Both of them are located at the same side of line C. Both of them are located at the left side of line C. For that reason, they are defined as one-sided angles. And why are angles alpha and beta defined as interior angles? The reason for that is because of the fact that they are located inside the structure of lines, inside the structure inside lines, the structure of lines A, C, and B. They are located inside this structure of lines A, C, B. For that reason, they are defined interior angles. Okay, so those two angles are one-sided interior angles. And we also have another type of angles that are one-sided interior angles. Actually, if we have two lines, line A, this is line A, and this is line B, and line C intersects those two lines. Line C in the red color, this is line C. Line C intersects those two lines A and B. Angles alpha and beta are defined as one-sided exterior angles. Okay, so I write it down. Angles alpha and beta are defined as one-sided exterior angles. Okay, those two angles alpha and beta are defined as one-sided exterior angles. Again, the reason that they are defined interior angles, the reason that they are defined one-sided angles is because of the fact that they are located at the same side. Both of them are located at the same side of line C. Both of them are located at the left side of line C. For that reason, they are defined as one-sided angles. And because of the fact that they are located outside of this structure of lines A, C, B, they are located outside of this structure of lines A, C, B, they are defined exterior angles. Okay, and we have a rule number 1. Rule number 1 states that if the sum of the two one-sided when I say one-sided, I relate to interior, one-sided interior angles and also one-sided exterior angles. it applies to both of those two angles. So if two one-sided, they can be interior or exterior. Angles equals to 180 degrees. Then line A is parallel to line B. Okay, so I will read rule number 1 again. Rule number 1 states that if the sum of the two one-sided angles equals to 180 degrees, then line A is parallel to line B. Okay, so actually here, if the sum of those two one-sided exterior angles equals to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Okay, if the sum of those two angles, alpha plus beta, equals to 180 degrees, we can deduce from it, according to rule number 1, that line A is parallel to line B. According to rule number 1. And the same rule is also true for one-sided interior angles. Those one-sided interior angles, we can apply rule number 1 also to the one-sided interior angles, and if the sum of alpha plus beta, that is to say, if alpha plus beta equals to 180 degrees, then we can deduce from it that line A is parallel to line B, according to rule number 1. So, as I've already told you, rule number 1 apply to both interior angles and exterior angles. Okay, those two one-sided angles are interior angles, and if the sum of those two angles equals to 180 degrees, then line A is parallel to line B, and also it applies to exterior one-sided angles. Those two exterior one-sided angles, if the sum of them, that is to say, if alpha plus beta equals to 180 degrees, we can deduce from it that line A is parallel to line B, according to rule number 1. Okay. So we actually can implement rule number 1 in our circle, because actually we have two one-sided angles. Those two angles are one-sided angles because of the fact that they are located at the right side of line segment DC. You can view AD is line A, PC is line B, and DC is line C that intersects those two lines. And because of the fact that those two angles, angle ADC and angle BCD, are located from the left side of line segment DC, they are defined as one-sided angles, and because of the fact that they are located inside the structure of lines AD, BC, and DC, they are defined as interior angles. And actually the sum of those two angles, angle ADC plus angle BCD, equals to 180 degrees. Okay, it is given us in the question that those two angles are right angles, so angle ADC this angle equals to 90 degrees, and also angle BCD equals to 90 degrees. So the sum of those two angles, 90 degrees plus 90 degrees, equals to 180 degrees. And as I've already told you, those two angles are one-sided interior angles. Okay? And they are one-sided interior angles. Okay, so we actually have in this drawing two one-sided interior angles, and the sum of those two one-sided interior angles is equal to 180 degrees. Okay, 90 degrees plus 90 degrees equals to 180 degrees. And therefore, according to rule number 1, line segment AD is parallel to line segment BC. Okay, so I write it down. According to rule number 1, line segment AD is parallel to line segment BC. So I will read again the Fields letter O. Angle ADC is a right angle, it equals to 90 degrees. This is a right angle, and also angle BCD is equals to 90 degrees. This angle is also a right angle, and the sum of those two angles, 90 degrees plus 90 degrees, equals to 180 degrees. Okay, and those two angles are interior one-sided angles because of the fact that they are located on the right side of line segment DC, both of them. So we have one-sided interior angles, that the sum of those two one-sided interior angles is equal to 180 degrees. So according to rule number 1, line segment AD is parallel to line segment BC. Okay. Okay, so those two line segments are parallel to each other. So in the next step, we will connect together points A and C by a straight line. Okay, we connected together points A and C by a straight line, and we will also connect together points B and D by a straight line. Okay, we connected together points D and B by a straight line, and we will call to the intersection point between line segment AC to line segment DB. We will call to the intersection point this point O. Okay, the intersection point between line segment AC and line segment DB is defined as point O. Okay. I will explain you the theorem of vertex angles. Okay. What are vertex angles? Okay. I will explain you the theorem of vertex angles. Actually, whenever two lines are intersecting each other, for example, if line A intersects with line B, actually at the intersection point, at this point, they create four angles. This is angle number 1. This is angle number 2. This is angle number 3. And this is angle number 4. Okay, whenever two lines are intersecting each other, they create four angles. 1, 2, 3, and 4. Okay. Actually, we have here two pairs of vertex angles. Angles 1 and 3 are defined as vertex angles. I will write it down. Angles 1 and 3 are defined as vertex angles. So that is the first pair of vertex angles, and we have the second pair of vertex angles that are actually angles 2 and 4. angles 2 and 4 are also vertex angles. So here we actually have two pairs of vertex angles. The first pair of vertex angles are 1 and 3, and the second pair of vertex angles are 2 and 4. So I'll read again the things that I wrote. Angles 1 and 3 are vertex angles. Those two angles are vertex angles. So that is the first pair of vertex angles, and also angles 2 and 4 are also vertex angles. And the second pair of vertex angles are angles 2 and 4. And we actually have a rule on vertex angles, rule number 2. According to rule number 2, or rule number 2 states that vertex angles are equal to each other. Vertex angles are equal to each other. So I will read rule number 2 again. According to rule number 2, vertex angles are equal to each other. So actually in this drawing, angles 1 and 3 are defined as vertex angles, and therefore they are equal to each other. Okay, so I can write here that angles 1 and 3 are defined as vertex angles, and according to rule number 2, according to rule number 2, vertex angles are equal to each other. So angle 1 equals to angle 3, and we have the second pair of vertex angles that are 2 and 4. Those two vertex angles are also equal to each other. That is to say, angle 2 equals to angle 4. Because both of those two pairs are vertex angles, and vertex angles are equal to each other according to rule number 2. Okay, so the first pair of vertex angles that are equal to each other are angles 1 and 3, those two angles, and they are equal to each other according to rule number 2. And the second pair of vertex angles that are equal to each other are angles 2 and 4. They are equal to each other according to rule number 2. Okay, so now I will draw separately the two pairs of vertex angles. So, as I already told you, whenever two lines are intersecting each other, they create two pairs of vertex angles at the intersection point. if this is line A, line A intersects with line B, this is line B, this is line B, so those two lines A and B are intersecting each other at this point. So the first pair of vertex angles are alpha and beta, and alpha equals to beta according to rule number 2. Okay, and we also have the second pair of vertex angles that are equal to each other. We have here two vertex angles that are also equal to each other. I will draw them separately. So the second pair of vertex angles that are equal to each other are alpha equals to beta according to rule number 2. Okay, angle alpha equals to beta because both of them are vertex angles and they are equal to each other according to rule number 2. So this is the second pair of vertex angles that are equal to each other, and also the first pair of vertex angles are also equal to each other according to rule number 2. Okay, so we actually can implement rule number 2 in our circle because we have in our circle actually here we have two pairs of vertex angles that are equal to each other, but we will focus only on one pair of vertex angles that are equal to each other. Those two angles are vertex angles and therefore they are equal to each other. So actually this angle AOD equals to angle BOC, because they are vertex angles and according to rule number 2 they are equal to each other. Okay, those two angles are equal to each other because they are vertex angles and according to rule number 2 they are equal to each other. Okay, angle AOD equals to angle BOC because they are vertex angles. Those two angles are vertex angles and according to rule number 2 they are equal to each other. Okay. In the next step, we will define a new term. We will define the term of alternating angles. Alternating angles. What are alternating angles? Okay. What are alternating angles? Actually, if we have two lines, line A and line B, this is line A and this is line B, and line C intersects those two lines. Line C intersects those two lines. The intersection point between line C and line A is at this point, and the intersection point between line C and line B is at this point. Angles alpha and beta are defined as interior alternating angles. Again, angles alpha and beta are defined as interior alternating angles. So I write it down. Angles alpha and beta are defined as interior alternating angles. Okay, angles alpha and beta are defined as interior alternating angles. First of all, why are angles alpha and beta are defined as alternating angles? The reason for that is because of the fact that they are located at different sides in relation to line C. While angle alpha is located on the left side of line C, angle beta is located on the right side of line C. So because of the fact that they are located at different sides of line segment C, they are defined alternating angles. And they are interior angles because of the fact that they are located inside the structure of lines A, C, and B. They are inside the structure, for that reason they are defined interior angles. So that is the first type of alternating angles, and we also have the second type of alternating angles that are called exterior alternating angles. And again, if we have two lines, line A and line B, and we have line C that intersects those two lines A and B. Line C intersects those two lines A and B. Angles alpha and beta are defined as exterior alternating angles. Again, angles alpha and beta are defined as exterior alternating angles. I write it down. Angles alpha and beta are defined as exterior alternating angles. Okay. First of all, why are angles alpha and beta are alternating angles, or defined as alternating angles? The answer to that question is very simple, because of the fact that they are located at different sides of line C. They are defined as alternating angles. While angle alpha is located to the left side of line C, angle beta is located to the right side of line C. So because of the fact that they are located at different sides in relation to line C, they are defined as alternating angles, and they are defined also as exterior angles because they are located outside of this structure of lines A, C, and B. They are outside of this structure of lines. For that reason, they are defined as exterior angles. Okay? And we actually have a rule number 3 for alternating angles. Rule number 3 states that alternating angles and it doesn't matter at all if they are interior or exterior. It relates to interior and also to exterior. Alternating angles between parallel lines are equal to each other. So I read rule number 3 again. Rule number 3 states that alternating angles, and it doesn't matter at all if they are interior alternating angles or exterior alternating angles, it applies to both of them. So alternating angles between parallel lines are equal to each other. So actually, here in the drawing we have two exterior alternating angles, and if line A is parallel to line B, then alpha equals to beta. Okay, if line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. Okay, if line A is parallel to line B, if those two lines are parallel to each other, then angle alpha equals to angle beta. Okay, and the same rule is true for interior alternating angles. Those two interior alternating angles, the same rule number 3 also applies to them. If line A is parallel to line B, if those two lines are parallel to each other, then according to rule number 3, angle alpha equals to angle beta. According to rule number 3. Okay. And also in the exterior angles, if line A is parallel to line B, then angle alpha equals to angle beta according to rule number 3. Okay, so we actually can apply rule number 3 in our circle. First of all, we'll focus on two triangles. Triangle BOC and triangle BOA. Triangle BOC and triangle AOD. I will paint the triangles that we will focus on. We will focus on the green triangle BOC, and we will also focus on the small green triangle AOD. Okay, so we will focus on the two green triangles. We have already proved that angle AOD equals to angle BOC because they are vertex angles, and according to rule number 2, they are equal to each other. Those two angles that I marked in the red color are equal to each other because they are vertex angles, and according to rule number 2, vertex angles are equal to each other. So I write it down. Angle AOD equals to angle BOC. Those two angles are equal to each other because they are vertex angles. And according to rule number 2, vertex angles are equal to each other. will read again the things that I wrote. Angle AOD equals to angle BOC because of the fact that those two angles are vertex angles, and according to rule number 2 they are equal to each other. Because vertex angles are equal to each other according to rule number 2. Okay, and also angle DAO, this angle equals to angle BCO, to this angle. Actually, those two angles are equal to each other. So I'll write down that angle DAO this angle DAO equals to angle BCO. Because of the fact that those two angles are alternating angles. Why are they alternating angles? Because they are located at different sides of line segment AC. Okay, those two angles are located at different sides of line segment AC. For that reason, they are defined as alternating angles, and they are also located between parallel lines. According to rule number 1, we have already proved that line segment AC is parallel to line segment AD is parallel to line segment BC. So those two alternating angles are located between parallel lines, and therefore they are equal to each other according to rule number 3. Okay, so angle DAO and angle BCO are alternating angles. And according to rule number 3, they are equal to each other. Because of the fact that those two alternating angles are located between parallel lines. Line segment AD is parallel to line segment BC. Line segment AD is parallel to line segment BC. Therefore, those two alternating angles that are located between parallel lines are equal to each other according to rule number 3. Okay, because according to rule number 3, alternating angles between parallel lines are equal to each other, and those two angles are alternating angles, and they are located between parallel lines. Line segment AD is parallel to line segment BC, therefore they are equal to each other according to rule number 3. Okay, so I write it down that angle DAO equals to angle BCO. Those two angles are equal to each other because of the fact that they are alternating angles, and they are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, the alternating angles that are located between parallel lines are equal to each other according to rule number 3. Okay? And also, angle CBO, this angle equals to angle ADO. Okay, those two angles are equal to each other because of the fact that there are two alternating angles. They are located at different sides of line segment DB. They are located at different sides of line segment DB, and they are located between parallel lines. Line segment AD is parallel to line segment BC. Therefore, because of the fact that there are alternating angles that are located between parallel lines, according to rule number 3, they are equal to each other. Okay, so actually those two angles are equal to each other exactly for the same reason that those two angles are equal to each other, because both of them are alternating angles that are located between parallel lines. According to rule number 3, alternating angles that are located between parallel lines are equal to each other. So we can write down that angle ADO equals to angle CBO because of the fact that they are alternating angles. And according to rule number 3, alternating angles that are located between parallel lines are equal to each other. Those two alternating angles are located between parallel line segments. Line segment AD is parallel to line segment BC, so those two alternating angles are alternating angles that are located between parallel lines. Therefore, they are equal to each other according to rule number 3. So here I wrote that angle ADO is equals to angle CBO. Those two angles are equal to each other because of the fact that they are alternating angles that are located between parallel lines. Therefore, they are equal to each other according to rule number 3. Okay. So we actually proved that three angles of this big green triangle are equal to three angles of this small green triangle, because those two angles are equal to each other, those two angles are also equal to each other, and those two angles are also equal to each other. So three angles of this big green triangle are equal to three angles of this green small triangle. Therefore, those two green triangles are similar to each other. Okay. Because whenever you prove that three angles of one triangle are equal to three angles at another triangle, you actually proved that those two triangles are similar to each other. Okay, so we can write down that this triangle BCO, is similar to triangle AOD. According to the rule of angle. Okay. I wrote A that is abbreviation for angle. So actually triangle BCO is similar to triangle AOD. According to the rule of angle. We prove that three angles at one triangle are equal to three angles of another triangle. For that reason, we prove that those two green triangles are similar to each other. And actually, when we have two triangles that are similar to each other, we have special relationship between their sides. So for example, if we have two triangles that are similar to each other, if triangle ABC if this triangle ABC is similar to triangle DEF, if the big triangle ABC is similar to the small triangle DEF, then we have a special relationship between their sides. That is to say, AB over DE equals to AC over DF AC over DF equals to BC over EF. Okay, so if the big triangle ABC is similar to the small triangle DEF, then the following relationship exists between their sides. AB over ED equals to AC over DF equals to BC over EF. Okay, again, AB over AD equals to AC over DF equals to BC over EF. Okay, so in our drawing, if we implement this rule of similar triangles, we can say that OB over OD OB over OD equals to OC over OA equals to BC over AD. Again, the following relationship exists between those two similar triangles. OB over OD, OB over OD equals to OC over OA equals to OC over OA equals to BC over AD equals to BC over AD. Okay? Again, OB over OD equals to OC over OA equals to BC over AD. Okay? But we know that BC equals to 8 units and AD equals to 4 units. It is given us in the question. So we can write here that BC equals to 8 units and AD equals to 4 units. And actually 8 over 4 is 2. Okay, so we got this equality. From this big equality we can derive two small equalities. The first equality that we can derive from this big equality is that OB over OD equals to 2. Okay, OB over OD equals to 2. Okay, we can multiply this equality by OD and we will get that OB equals to 2 times okay, we will get that OB equals to 2 times OD. Okay, OB equals 2 times OD. OB equals 2 times OD. So if we define OD as A, that is to say OD equals to A, then OB equals 2 times OD. OB equals 2 times OD, but OD equals to A, so OB that equals 2 times OD equals to 2 times A. Okay, and the second equality that we can derive from this equality is that OC over OD also equals to 2. Okay, OC over OD equals to 2. I'll write it down, OC over OA equals to 2. Okay, OC over OA equals to 2. We can multiply this equality by OA and we will get that OC equals 2 times OA. OC equals 2 times OA. OC equals 2 times OA, so if OA equals to B, then OC equals 2 times OA. OC will be equal 2 times OA, and OA equals to B, so OC equals 2 times B. Okay, okay, and in the next step we will find out the values of A and B by the Pythagorean theorem. Angle ADC equals to 90 degrees. Angle ADC equals to 90 degrees. If angle ADC equals to 90 degrees, then triangle ADC is a right triangle. Okay, triangle ADC is a right triangle. Okay. So we can implement the Pythagorean theorem on this right triangle ADC. According to the Pythagorean theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of triangle ADC is AC, so the square of the hypotenuse equals to AC square. The square of the hypotenuse equals to the sum of the squares of the perpendiculars equals to AD square plus DC square. So according to the Pythagorean theorem in the right triangle ADC, we have this equality that AC square, the square of the hypotenuse, equals to AD square plus DC square. Okay? But what is the value of AC? The value of AC equals to OA plus OC. The value of AC equals to OA plus OC, but OA equals to B and OC equals to 2B. So in total OC will be equal to B plus 2B. That is to say OC equals to 3B. Okay, AC equals to 3B. So AC square is B square. Okay, AD equals to 4 units. So AD square is 4 square, 4 square is 16, plus DC square. DC equals to 6, so 6 square is 36. So in total we got that 3B square equals to 16 plus 36. 16 plus 36 equals to 52, so I write it down. 3B square equals to 52. Okay, 3B square equals to 52. The next step, we will take a root out of this equality. We will get that 3B equals to the root of 52. But we know that 52 equals to 13 times 4. And we can split the roots to 2 roots according to the rule that the root of a times b equals to the root of a times root b. Okay, so 3b will be equal to the root of 4 times root of 13. Okay, 3b equals to the root of 4 times root 13. The root of 4 is 2, so I write it down. In total, we got that 3b equals to 2 times root 13. The next step, we will divide this equality by 3 in order to get the value of b. So b equals to 2 over 3 times root 13. If b equals to 2 over 3 times root 13, then 2b will be equal to 4 over 3 times root 13. Okay, we got that b equals to 2 over 3 times root 13, and if b equals to 2 over 3 times root 13, then 2 times b will be equal to 4 over 3 times root 13. So we can write here that b equals to 2 over 3 times root 13, and 2 times b equals to 4 over 3 times root 13. Okay. In the next step, we will do the same process. We'll repeat on the same process in order to find out the value of b. We know that angle BCD equals to 90 degrees. Angle BCD equals to 90 degrees. Therefore, triangle BCD is a right triangle. Triangle BCD is a right triangle. And we can implement the Pythagorean theorem in the right triangle BCD. According to the Pythagorean theorem, the square of the hypotenuse, that is to say db square, equals to the sum of the squares of the perpendiculars, equals to bc square plus dc square. Okay, so we implemented all the Pythagorean theorem in the right triangle BCD. Angle BCD is the right angle, so triangle BCD is a right triangle. So we implemented the Pythagorean theorem in the right triangle BCD that states that the square of the hypotenuse, that is to say db square, equals to the sum of the squares of the perpendiculars, equals to bc square plus dc square. Okay, but what is the value of db? The value of db equals to OD plus OB. OD plus OB equals to the value of dB, and OD equals to A and OB equals to 2A. So OD plus OB will be equal to A plus 2A. A plus 2A equals to 3A. So dB equals to 3A, so dB square will be equals to 3A square, and BC square, BC equals to 8 units, so BC square is 8 squared, 8 squared is 64. And we have DC equals to 6 units, so DC square is 6 squared, and 6 squared is 36. So in total, we got that 3 times A square equals to 64 plus 36. 64 plus 36 is 100, so I write it down. Okay, we got that 3a squared equals to 100. Now we'll take a root out of this equality. And the root of 100 is 10. So we'll get that 3a equals to the root of 100, that is 10. 3a equals to 10. So if 3a equals to 10, we can divide this equality by 3 in order to get the value of 3. So a will be equal to 10 over 3 units, and 2 times a will be equal to 20 over 3 units. Okay, so we can write here that a equals to 10 over 3 units, while 2 times a equals to 20 over 3 units. Okay, so we have found out all the values of all the line segments inside the circle. In the next step, we'll copy this drawing to this page without the a and b, and only with the values of a and b. Okay, because we already know the values of a and b, so we don't need the a and b in the drawing, because we found out the values of a and b. Okay, so we will draw again the drawing that we have. Okay, this is point O. We know that AO equals to 2 over 3 times root 13 units. While OC equals to 4 over 3 times root 13 units. And OD equals to 10 over 3 units, while OB equals to 20 over 3 units. Okay. In the next step, we'll extend line segment OC until it touches the circle at point P. Okay. Okay. So we extended line segment AC until it touches the circle at point P. Actually, point P is the point of contact between the circle and chord AP. Again, point P is the point of contact between the circle and chord AP. Okay, and in the next step we will calculate the value of the line segment CP that we created. In order to calculate the value of line segment CP, we need to state a new rule, rule number 4. According to rule number 4, if two chords are intersecting each other, if we have chord AB, this is chord AB, that intersects with chord CD, okay, chord AB intersects with chord CD at point O. The point of intersection between chord AB and chord DC is at point O. If this is the data that we have, then we can implement, then the following equality is true, that AO times AO times BO equals to CO times DO. I'll write it down. AO times BO equals to CO times DO. Okay. AO times BO equals to CO times DO. Okay, so if two chords are intersecting each other at point O, then the following equality is true, that AO times OB equals to CO times OD. So I write down rule number 4. According to rule number 4, or rule number 4 states that if two chords are intersecting each other at point O, if two chords, that is to say chord AB and chord CD, AB and CD, are intersecting each other at point O, at point O. Point O is the point O is the point of intersection between chord AB and chord CD. Point O. Then if this is the reality, then the following equality is true. Then the following equality is true. That AO times BO equals to CO times DO. I will read rule number 4 again. Rule number 4 states that if two chords, chord AV and chord CD, are intersecting each other at point O. Point O is the point of intersection between chord AB and chord CD. Then the following equality is true. So if this is the data that we have, the two chords are intersecting each other at point O, then the following equality is true. That AO times VO equals to CO times DO. AO times VO equals to CO times DO. Okay? Okay, so we actually can implement rule number 4 in our circle. Because in our circle we have chord AP intersects with chord DB at point O. I write it down. Chord AP intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Again, AO times OP equals to DO times OB. So I read again the things that I wrote. So in our drawing, we have chord AB that intersects with chord DB at point O. Okay, chord AP, this chord intersects with chord DB at point O. Point O is the point of intersection between chord AP and chord DB. Therefore, according to rule number 4, AO times OP equals to DO times OB. Okay, again, AO times OP equals to DO times OB. Okay, AO equals to 2 over 3 times root 13. And OP equals to OC plus CP. Again, OP equals to OC plus CP. All equals to DO. DO is 10 over 3. times OB. OB is 20 over 3 units. So in total we got that 2 over 3 times root 13 times OC plus CP equals to 10 over 3 times 20 over 3. But what is the value of OC? The value of OC is 4 over 3 times root 13, so I write it down. So OC equals to 4 over 3 times root 13. OC equals to 4 over 3 times root 13. So in total we got that 2 over 3 times root 13. In the brackets we have 4 over 3 times root 13 plus CP equals to 10 over 3 times 20 over 3. Here we have 3 in the denominator of this side of the equation, and we have 3 in the dominator. We have 3 in the denominator of the other side of the equation, so we can cancel 3. Okay, because we have 3 in the denominator of this side of the equation and 3 in the denominator of the other side of the equation, so we can cancel 3. And what is left after we cancel 3 is so we have here 2 times root 13 times 4 over 3 times root 13 equals to 10 times 20 over 3. Actually 10 times 20 is 200, and 10 times 4 is 8, and we have root 13 in the numerator and we have root 13 in the denominator, so we can cancel root 13. Actually, root 13 times root 13 is 13. 13 is not cancelled, but root 13 times root 13 equals to 13. okay, and so in total we got that 8 times 13 over 3 equals plus 2 times root 13 times CP equals to 200 over 3. 8 times 13 is 104, so I write it down. So in total we got that 104 over 3 plus 2 times root 13 times CP equals to 200 over 3. Now we will subtract 104 over 3 from both sides of the equations. So we subtracted 104 over 3 from both sides of the equation, and 104 over 3 minus 104 over 3 is 0, so what is left in this side of the equation is 2 times root 13 times root times CP equals to 200 over 3 minus 104 over 3. And here we can take a common factor 3 in the denominator of this expression. So we took a common factor 3 in the denominator of this expression. So we got the 200 minus 104 is 96 over 3. and 96 over 3 is 32. So I write it down. So we got that 2 times root 13 times CP equals to 32. We will divide this equality by 2. We'll get that we divided this equality by 2. We got that root 13 times CP equals to 16. We divide this equality by root 13 and we will get the value of CP. So we got that the value of CP is 16 over root 13 units. So we can write here that the value of CP is 16 over root 13 units. Okay, the value of CP is 16 over root 13 units. In the next step, we will extend line segment DC until it touches the circle at point Q. Okay, we extended line segment DC until it touches the circle at point Q. Q is the point of contact between the circle and chord DQ. Again, Q is the point of contact between the circle and chord DQ. We will calculate the value of CQ. We will calculate the value of CQ according to the fourth rule, because we actually have chord DQ intersects with chord AP at point C. I write it down. Chord DQ intersects with chord AP at point C. Point C is the point of intersection between chord DQ and chord AP. So according to the fourth rule, or according to rule number 4, therefore according to Rule number 4. According to rule number 4, AC times CP equals to DC times CQ. Again, AC times CP equals to DC times CQ. So I will read again the things that I wrote. Chord DQ intersects with chord AP at point C. Chord DQ intersects with chord AP at point C. Point C is the point of intersection between chord DQ and chord AP. Therefore, according to rule number 4, AC times CP equals to DC times CQ. AC times CP equals to DC times CQ. Okay? Again, AC times CP equals to DC times CQ. AC equals to 2 over 3 times root 13 plus 4 over 3 times root 13. In total it equals to 6 over 3 times root 13. Times CP. CP equals to 16 over root 13 units. All equals to DC. DC equals to 6 units. And CQ is the missing line segment. So I will leave it as it is. So in total we got that 6 over 3 times root 13 times 16 over root 13 equals to 6 CQ. Now we have root 13 in the numerator and we have root 13 in the denominator. So root 13 is cancelled and 6 over 3 is 2. Okay, so in total we will get that 2 times 16 equals to 6 times CQ. Okay, here we have only 2 times 16 because root 13 is cancelled. So 2 times 16 equals to 6 CQ. Okay, 2 times 16 equals to 6 CQ. 2 times 16 is 32. So I write it down. 32 equals to 6 CQ. We will divide this equality by 6 and we will get that CQ equals to 32 over 6. Okay, CQ equals to 32 over 6. We can divide the numerator and the denominator by 2, okay, because T2 is common factor between the denominator and between the numerator and the denominator. We get that CQ equals to 16 over 3 units. So the value of CQ is 16 over 3 units, so we can write here that the value of CQ is 16 over 3 units. Okay, in the next step we will extend line segment BC until it touches the circle at point R. We extended line segment BC until it touches the circle at point R. Point R is the point of contact between the circle and chord BR. Okay? We will find the value of RC according to the fourth rule. We have chord DQ that intersects with chord RB at point C. Again, I'll write it down. Chord DQ intersects with chord RB at point C. Again, chord DQ intersects with chord RP at point C. Point C is the point of intersection between chord RB and chord DQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. So I'll read again the things that I wrote. Chord DQ intersects with chord RB at point C. Chord DQ intersects with chord RB at point C. Point C is the point of intersection between chord DQ and chord RB. Therefore, according to rule number 4, RC times BC equals to DC times CQ. Therefore, according to rule number 4, RC times BC equals to DC times CQ. Okay, so RC equals to 6 units. RC is the missing line segment. RC is the missing line segment. So we leave it as it is. BC equals to 8 units. Equals to DC equals to 6 units. And CQ equals to 16 over 3 units. Okay, in total we got that 8 times RC equals to 6 times 16 over 3. 6 over 3 is 2, so I write it down. So we got that 8 times RC equals to 2 times 16. 2 times 16 is 32, so I write it down. We got that 8 RC equals to 32. We will divide this equality by 8 in order to get the value of RC. 32 over 8 is 4. So the value of RC is 4 units. So RC equals to 4 units. So I write it down. RC equals to 4 units. Okay. So actually we found out all the line segments inside the circle, and the only missing variable is the radius of this circle, or the only missing thing is the radius of this circle. In order to find the radius of this circle, we will state a new rule, rule number 5. Actually, rule number 5 states that if two chords are intersecting each other at 90 degrees, so if chord AB, this is chord AB that intersects with chord CD, chord AB intersects with chord CD at 90 degrees. So they create at the intersection point 90 degrees. Actually, all the angles here are right angles, and the intersection point will be called point O. So if this is the reality, this is the data that we have, then according to rule number 5, the following equality is true, that 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. So whenever two chords are intersecting each other at 90 degrees, at the point of intersection they create between them 90 degrees, then the following equality is true, that 4 times the radius of the circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. So I will write down rule number 5. According to rule number 5, if two chords are intersecting each other, if two chords, that is to say chord AB and chord CD, AB and CD. Are intersecting each other. Each other at 90 degrees, and the point of intersection is point O. So if that is the data that we have, then the following equality is true. Four times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus CO squared plus DO squared. So I will read rule number 5 again. Rule number 5 states that if two chords, that is to say chord AB and chord CD, those two chords, chord AB and chord CD, are intersecting each other at 90 degrees, at the point of intersection they create between them 90 degrees. Actually all the angles around point O are right angles equal to 90 degrees. Okay, at point O, the point of intersection is point O. Then the following equality is true. That 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay? So actually we can implement rule number 5 in our circle. Because in our circle we have called the actual, first of all, angle BCD equals to 90 degrees. Okay, and chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord RB intersects with chord DQ at 90 degrees. At the intersection point at point C, they create 90 degrees between them. Because, as I already told you, angle BCD is 90 degrees. So, they create 90 degrees at the intersection point between DQ to RB. They create 90 degrees between them. Okay? At point C, the point of intersection is at point C. Therefore, according to rule number 5, four times the radius of this circle squared equals to RC square plus BC square plus DC square plus CQ square. So I will read again the things that I wrote. Angle BCD is a right angle. It is given us in the question that angle BCD is a right angle. It equals to 90 degrees. And chord RB intersects with chord DQ at 90 degrees. Chord RB intersects with chord DQ at 90 degrees. This angle is 90 degrees, and all the angles around point C are right angles. They are equal to 90 degrees. At point C, the point of intersection between DQ to RB is at point C. Therefore, according to rule number 5, 4 times the radius of this circle squared equals to RC square plus BC square plus DQ square plus CQ square. Okay? So, actually, 4 times the radius of the circle squared equals to RC square. RC equals to 4 units, so RC square equals to 16 plus BC square. BC equals to 8. 8 square is 64 plus DC square. DC equals to 6, so DC square is 36 plus CQ square. CQ equals to 16 over 3 units. 16 over 3 is 5/3, and 5/3 squared is 28.444. So, in total we got that 4 times the radius of the circle squared, or the radius of our circle squared, equals to 16 plus 64 plus 36 plus 28.444. 64 plus 36 is 100. 100 plus 16 is 116, and 116 plus 28.444 equals to 144.444. So I write it down. In total we got that 4 times the radius of the circle squared equals to 144.444. Okay. So we got that 4 times the radius of the circle squared equals to 144.444. Now we divide this equality by 4 in order to get the value of r squared. We get that r squared equals to 36.111. Okay, we got that r squared equals to 36.111. Now we know that the area, the formula for the area of any circle equals to pi times the radius of the circle squared. So the area of a circle equals to pi times r square. So the formula for the area of any circle equals to pi times the radius of the circle square. But we know that r square equals to 36.111, so we can substitute r square by 36.111 and we will get the area of our circle. Okay, so the area of our circle equals to pi times 36.111 square units. So we substituted r square by 36.111 and we got that the area of our circle equals to pi times 36.111 square units, or in terms of numbers, the area of the circle equals to 113.45 square units. Okay, the area of our circle equals to 113.45 square units. Okay, the area of the circle equals to 113.45 square units. Now I'll summarize the lecture. Actually, we wanted to find out the area of this circle, and we know that inside the circle we have a shape. This angle of this shape is 90 degrees, and also angle BCD equals to 90 degrees, and side AD of this shape equals to 4 units, side EC equals to 6 units, and side BC of this shape equals to 8 units. And we want to find out the area of this circle. Okay? So, in order to find out the area of this circle, first of all, we must explain you what are one-sided angles. Okay? Actually, if we have line A and line B and line C intersects those two lines A and B, angles alpha and beta are defined as one-sided interior angles. Okay, they are in one-sided angles because they are located at the same side of line C. They're both located on the right side of line C, and they are interior angles because they are located inside this structure of lines. Okay, so those two angles alpha and beta are defined as interior one-sided angles, while those two angles alpha and beta are defined as exterior alternating angles because they are one-sided angles because both of them are located at the right side of line C, and they are exterior angles because they are outside of this structure of lines A, C, and B. Okay, and we have rule number 1 that states that if the sum of the two one-sided angles equals to 180 degrees, then A equals to B. Okay, so if alpha plus beta equals to 180 degrees, then line A is parallel to line B. Those lines are parallel to each other. And the same rule number 1 applies also to one-sided interior angles. If the sum of those two angles is equal to 180 degrees, then line A is parallel to line B. Those two lines are parallel to each other. Okay, and we implemented rule number 1 in our circle because actually we have those two angles that are one-sided interior angles. They are one-sided angles because both of those angles are located at the right side of line segment DC, and they are interior angles because they are inside the structure of line and the structure of segment lines AD, DC, and BC. So the sum of those two one-sided angles equals to 180 degrees because each angle is 90 degrees, so 90 degrees plus 90 degrees is 180 degrees. So the sum of those two one-sided angles equals to 180 degrees. So according to rule number 1, line segment AD is parallel to line segment BC. Okay, because you can view AD as line A, BC as line B, and DC as line C that intersects those two lines at line C and at point C and at point D. Okay, so because of the fact that the sum of those two one-sided interior angles equals to 180 degrees, according to rule number 1, line segment AD is parallel to line segment BC. Okay, so we proved that those two line segments are parallel to each other, and then we defined the theorem of vertex angles. If two lines are intersecting each other and this is the intersection point, they create four angles, 1, 2, 3, and 4. They actually create two pairs of vertex angles. The first pair of vertex angles are 1 and 3, and the second pair of vertex angles are 2 and 4. Okay, so angles 1 and 3 are defined as vertex angles, and also angles 2 and 4 are defined as vertex angles. And we have rule number 2 that states that vertex angles are equal to each other. So actually here, this drawing, angle 1 is equals to angle 3 because they are vertex angles, and also angle 2 equals to angle 4 because they are vertex angles, and according to rule number 2, vertex angles are equal to each other. Okay? So actually I draw them separately. I draw the two pairs of vertex angles separately. Those are the first pair of vertex angles that are equal to each other according to rule number 2, and those vertex angles are second pair of vertex angles, and they are also equal to each other according to rule number 2. Okay, so we actually can implement rule number 2 in our circle, because we have, before that I must mention that we connected points C and B by a straight line, and we also connected points A and C by a straight line, and then we have those two angles that are defined as vertex angles, and according to rule number 2 they are equal to each other. Okay, and then we defined the theorem of alternating angles. If we have line A and line B and line C intersect those two lines A and B, actually those two angles alpha and beta are defined as alternating angles because of the fact that they are located at different sides of line C. Angle alpha is located at the right side of line C, while angle beta is located at the left side of line C. For that reason they are defined alternating angles, and they are located inside the structure of lines A, C and B. For that reason they are defined interior angles. So those angles are interior alternating angles. Those are the first type of alternating angles, and we also have the second type of alternating angles. Those two angles are exterior alternating angles. Again, why are they alternating angles? Because they are located at different sides of line C. While angle alpha is located to the right side of line C, angle beta is located to the left side of line C. And they are exterior angles because they are located outside of the structure of lines A, C and B. Okay? And we have rule number 3 that states that alternating angles between parallel lines are equal to each other. So those two exterior alternating angles, they will be equal to each other only if line A is parallel to line B, or if we know that line A is parallel to line B, then according to rule number 3, angle alpha equals to angle beta. So if we know that A is parallel to B, or line A is parallel to line B, then angle alpha equals to angle beta. And the same rule also true for interior alternating angles. If we know that line A is parallel to line B, then we can deduce from it, according to rule number 3, that angle alpha equals to angle beta. Okay? So we actually implemented rule number 3 in our circle. We focused on the green triangles, and on the two green triangles we have already proved that those angles are equal to each other because they are vertex angles, and according to rule number 2, vertex angles are equal to each other. And also those two angles are equal to each other because of the fact that they are alternating angles. They are located at different sides of line segment AC. For that reason, they are alternating angles, and they are located between two line segments that are parallel to each other. Line segment AD is parallel to line segment BC. So those two alternating angles are located between parallel line segments, therefore they are equal to each other according to rule number 3. And we also have those two angles that are equal to each other because of the fact they are alternating angles because of the fact that they are located at different sides of line segment DB. Okay? And they are located between parallel lines. Line segment AD is parallel to line segment DC, therefore those alternating angles that are located between parallel lines are equal to each other according to rule number 3. So we actually proved that those two angles are equal to each other, those two angles are equal to each other, and also those two angles are equal to each other. So we actually proved that three angles in this big green triangle are equal to three angles on this small green triangle. Therefore, we actually proved that those two green triangles are similar to each other according to the rule of angle, angle, angle. When you prove that three angles of one triangle are equal to three angles of other triangles, we prove that those two triangles are similar to each other. Okay, so those two green triangles are similar to each other, and whenever you have two similar triangles and you have a special relationship between the sides of those similar triangles. For example, if you have two triangles that are similar to each other, the big triangle you see is similar to the small triangle DEF, then the following relationship exists between them: AB over DED, AB over AD equals to AC over DF equals to BC over EF. Okay, so we actually can say that in our two green similar triangles that OB over OD, OB over OD equals to OC over OA and equals to BC over AD. Okay, OB over OD equals to OC over OA equals to BC over AD. But we know that BC equals to 8 units and AD equals to 4 units. Okay, so we can write here that BC equals to 8 and AD equals to 4. And 8 over 4 is 2. So we have this big equality. We can derive from it two small equalities. The first equality is that OB over OD equals to 2, and if OB over OD equals to 2, then OB equals 2 times OD. OB equals 2 times OD, so if OD equals to A, then OB equals 2A. And we can derive the second equality that states that OC over OA equals to 2, and if OC over OA equals to 2, then OC equals to 2 times OA. OC equals 2 times OA, so if OA equals to B, then OC equals 2 times OA. OC equals to 2B, so if OA equals to B, then OC equals 2B. Okay, and we found out the values of A and B by implementing the Pythagorean theorem on the right triangle ADC. We know that angle ADC is 90 degrees. It is given us in the question, so therefore triangle ADC is a right triangle, so we can implement the Pythagorean theorem in the right triangle ADC. We can say that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. Okay, AC square equals to AD square plus DC square. we know that AC equals to 3B. We have the values of AD and DC. The only missing variable is B, so we found out that the value of B is 2 over 3 times root 13, while the value of 2B is 4 over 3 times root 13. Okay, and the next step, we also know that angle BCD is a right angle, it equals to 90 degrees, therefore triangle BCD is a right triangle, so we can implement the Pythagorean theorem in the right triangle BCD. According to the Pythagorean theorem, the square of the hypotenuse, that is to say dB square, equals to the sum of the squares of the perpendiculars, equals to BC square plus DC square. Okay, dB square equals to BC square plus DC square. And we know that dB equals to 3A and BC equals to 8 units and DC equals to 6 units, so the only missing variable is A. So we found out that the value of A is 10 over 3 units, while the value of 2A is 20 over 3 units. So we actually got all the values of all the line segments inside this circle. And we copied this drawing here. It is exactly the same without A and B, because we already know the values of A and B, so we don't need A and B. We extended line segment AC until it touches the circle at point P, and we found out the value of CP according to the fourth rule. The fourth rule states that if two chords are intersecting each other at point O, then the following equality is true. So if two chords, chord AB and chord AC, are intersecting each other at point O is the point of intersection between chord AB and chord CD, then the following equality is true, that OA over OB equals to CO over OD. Okay? So again, if two chords, chord AB and chord CD, are intersecting each other at point O, then the following equality is true, that OA over OB equals to OC over OD. Okay? So we implemented this rule in rule number 4 in our circle, because we have chord AP that intersects chord DQ at chord AP intersects chord DB at point O. Therefore, according to rule number 4, AO times OB equals to DO times OB. Again, AO times OB equals to DO times OB. Okay, and AO times OB equals to DO times OB, and we have all the values of all the line segments here. The only missing variable, the only missing line segment is CP, so we put the data inside this equality, and we found out that the value of CP is 16 over root 13 units. Okay, the value of CP is 16 over root 13 units. And then we extended line segment DC until it touches the circle at point Q. And we found out the value of CQ by implementing the fourth rule of this circle. We have chord DQ that intersects with chord AP at point C. Therefore, according to rule number 4, AC times CP equals to DC times CQ. Again, AC times CP equals to DC times CQ. And we actually have all the values of all the line segments. the only missing variable is CQ, and we found out that the value of CQ is 16 over 3 units. Okay, the value of CQ is 16 over 3 units, and then we extended line segment BC until it touches the circle at point R. And in order to find out the value of line segment RC, we implemented rule number 4 on this circle. We have chord DQ that intersects with chord RB at point C. Therefore, according to rule number 4, RC times CP equals to DC times CQ. Again, RC times BC equals to DC times CQ, and the only missing variable is RC. So we put the data inside this equality, and we found out that the value of RC is 4 units. So we found out all the values of all the line segments inside this circle, and the only missing thing is the radius of this circle. And in order to find out the radius of this circle, we implemented rule number 5 that states that if two chords are intersecting each other at 90 degrees at point O, then the following equality is true, that 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Again, 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, so I read again rule number 5. Rule number 5 states that if two chords are intersecting each other at 90 degrees at point O, then the following equality is true. That 4 times the radius of this circle squared equals to AO squared plus BO squared plus CO squared plus DO squared. Okay, actually we have chord in our circle, we have chord RB that intersects with chord DQ at 90 degrees, because we know that angle BCD is a right angle. It is given us in the question. So those two chords, chord DQ and chord RB, are intersecting each other at 90 degrees. Therefore, at point C, therefore, according to rule number 4, 4 times the radius of this circle squared equals to RC squared plus BC squared plus DC squared plus CQ squared. Okay? 4 times the radius of the circle squared equals to RC squared plus BC squared plus DC squared plus CQ squared. And we know all the values of all the line segments. The only missing variable is R. So we put the data inside this equality, and we found out that the radius of the circle squared equals to 36.111. And we know that the area of any circle equals to pi times the radius of the circle squared. And we found out that the radius of the circle squared equals to 36.111. So we can substitute R squared in the formula for the area of a circle by 36.111. So we substituted R squared by 36.111, and we found out that the area of our circle equals to pi times 36.111 square units. So the area of our circle in terms of numbers equals to 113.45 units. The area of this circle equals to 113.45 square units. Okay, thank you very much.